over to you.
Thank you, Rutger. Thank you, Damien, to everyone for making this presentation possible despite the harvesting time and the awful weather coming. Thank you all for being here as well. I don't know, I was about to introduce myself, but I think that's enough of introductions. I'm a geologist, I'm Spanish, I come from the Basque Country. My name is Itxaso, and yes, thanks to Damien, we had the opportunity to come to Blenheim, to the area of Marlborough, and to do this study that I'm about to present, and hopefully to engage you with the methodology we are using and apply it in the future. So what we did with Damien here was our work on soil-driven variability in grapevine water uptake depth across the 7 soil types in Marlborough. Just a bit of a context, although you're all from Marlborough, so you probably already know, but Marlborough has around 25,000 hectares of horticulture, 30 of which it's the same map as this one, 30 of which are planted vineyards. And despite the area receives a lot of rain, the shadow effect of the mountains actually gives the valleys, the lower floodplains, a dry climate. And because mostly Marlborough is interested in doing aromatic whites, it's interested in keeping high canopy densities to keep the grapes shaded and cool and fresh. And therefore, most of the vineyards in Marlborough are irrigated. Irrigation water, it's available. There's plenty of irrigation water, and it's mostly coming from the aquifers, mainly from the Wairau aquifer here in lila color. However, because the horticultural land is so extensive here in Marlborough, and it's mostly irrigated, there's a lot of pumping from the aquifers, and also due to the flood protection measures in place in the area, it actually it alters the natural hydrological connectivity of the aquifer, and it affects its replenishment. And therefore, there's this need to improve irrigation efficiency and soil water management to sustain viticulture in Marlborough. So, thinking about this need, we thought, okay, which would be the first step to achieve irrigation efficiency? So we thought that the first step would be to understand how soil properties and water availability shape grapevine water uptake. This is not a straightforward question, at least here in Marlborough, because there are at least 16 different soil types, and each of the soil type has a very different water footprint. And therefore, what we thought, mainly Damien, thought that we could maybe start with 7 different soil types spread across Marlborough. 5 of them are in the Wairau Valley and 2 of them in the Aguatere Valley, and they are of different ages and types. So there are recent soils, and there are then some clay and more mature soils. So we came here last year, and for a whole week, we were sampling during February, that was Verizon time, the different vineyards in the different 7 soils. So that became part of, yes, our methodology. The first thing that we did was to take a good look to the soil reports from Manaki Whenua, where the soil comes very well described. That actually, I guess, it helped deciding for the soils to sample. And then we came to Marlborough to sample the vineyards. We tasked Damien to put 3 of these rainfall collectors, which allow to take rain for a month, and then it doesn't allow it to evaporate again. So we had some samples of rain. We also took some samples of the dripping lines of all the 7 vineyards. There was 1 vineyard which was not irrigated, therefore we ended up with 6 samples. And then in each vineyard, what we did was, well, this is the interrow, and these things are the different grapevines. So we chose 3 grapevines which were well exposed to the sun, they were healthy, they were looking good. And then what we did was we cut 5 centimeters of the shot of the vineyard, always above the bunch, so we didn't affect any production and so on. We took 5 centimeters of each of the vineyards as a sample. I will explain now for what. Then we got 3 in each of the vineyards, so just to allow for reproducibility for the 7 vineyards. So we ended up with 21 samples. Then in between this triangle in the middle, we got 1 sample in each of the vineyards of a plant from the interrow. And lastly, we also took 1 soil core from the interrow of the vineyard. We went down to 130 centimeters in steps of 10 to 20 centimeters. And then we also took 3 more cores, 1 each below each of the sampled grapevine. So we ended up with quite a lot of samples from the soil. From these samples of the soil, we took a look to all of these properties: particle size distribution, pH, carbon and nitrogen. And I'm very quickly going to show you the results. Well, we also noted when we were in the field whether we were coring the soils with a manual corer. So we were also noting down when did we have subsoil compaction. We found subsoil compaction in the Renvik soil type at around 50 centimeters and 70 centimeters for the CB1 Pukeuri. These are the more mature soils. Sorry for my voice, I've been quite sick last week, so I'm still dealing with that. And the different things we've seen, it's the particle size distribution. Soils are generally very silt dominated, as you can see. Some of them have a little bit of sand towards the depth, and they're very low in clay in general, but Hinds and Temuka, which have up to 3%, I think, of clay. Then the blue line is the gravitational water content. It is fairly stable through the profiles, and it's always around 8 to 30 centimeters. It was higher in the recently fluvial soils, more towards the 30%, and it was a bit lower towards the mature soil. The gravity water-metric content, it normally correlates with the fines, so actually with the texture. Whenever there's more clay, the soil is capable of retaining more water, so it normally correlates with this. But in this case, for all the soils, it correlated better with the carbon and nitrogen ratio, which is down here, meaning that the organic matter actually controlled better the water retention than the texture. Carbon and nitrogen were also, as expected, were higher in the topsoil, and then they decrease with depth, just showing organic matter decomposition, and the pH of all the soils was below 10 generally. So that's for soil particles. That's for these samples from here. But then from the soil samples, from soil samples, and from all the other samples, what we did was, which actually is the topic composition of water. I will explain now what is that. But the thing was that we wanted to extract the water of all the different samples. How did we do that? First of all, we put all our samples. This one is soil, but the shots would come here, the root would come here. We put our sample in such a vial. We connect it to an empty vial. And then this empty vial, we put it in an extraction line that vacuums the vial at -1 pressure. So now there is a difference of pressure between one and the other vial. And then once the collection vial is vacuumed, we place it in liquid nitrogen, so really cold, and the sample vial, we place it at 150 degrees. Then, thank you, so nice. Thank you very much.
Yeah, no problem.
Then we have a difference in temperature between the vials and a difference in pressure as well. What we want to do is from the sample vial, we want to evaporate all the water and then get it transported to the other vial. Because of the difference of temperature, it will precipitate in the other vial, and because of the difference of pressure, it will trouble all the way. Why do we want to get the water from all of these samples? Well, we all know, it's a bit of a very short context, okay? But we all know that water is HO2. It's two elements, oxygen and hydrogen. And each element of the periodic table can have different weights, can weight more or less depending on the different processes that it's gone through, as for example, evaporation or precipitation. So each of the different processes that the water goes through will affect its weight. Therefore, if we have different waters from different places, each of the waters will have a very characteristic signature. So we will be able to differentiate them. So the first thing that we did was characterize all the different waters within all the different samples. And then the other nice thing is that the plant water, so grapevine or trees, as Rutger was saying, reflects the mix of the water that the plant that has accessed, right? So it doesn't alter, the plant doesn't alter the signature of the water that it's been drinking from, right? So we wanted to do exactly this. We wanted to characterize all the waters and compare it with the water from the plant. We did that for the 7 vineyards sitting in the 7 type of soils, and we got this. So if we take only one of them, just to understand better what these graphs say, the first thing we can look at is that these are the different characterization of the different samples. We have the rainfall, we have the grapevine, we have irrigation, and then all the soil at different depths, right? And this is the isotopic value. So the first thing we can see is that all soils, these are the soils from 0 to 130 centimeters, all soils have this evaporation curve, meaning that they are changing in isotopic value up here due to evaporation. That's the first thing we see, and that's really important for us to see within the different soils. That's the first thing we can see. The second thing we can see is that irrigation value. Irrigation water is isotopically similar to groundwater, which makes sense because we've said that most of the vineyards here in Marlborough are irrigated with groundwater. So that's within the expected. Also for the rain, remember that we had these rain traps. Rainfall falls within the reported values. There's a very nice study for Marlborough, for all New Zealand actually, and then they isotopically characterize rainfall throughout the whole year in the different areas within New Zealand. It fits perfect for summer type of rain here in Marlborough. And the interesting bit, we have here the signal of the grapevine and the signal of the interrow grass. The first thing we can see, I would go for this one first, is that the grapevine and the interrow grass, they fall within the range of soil water. You see these extended shadowed areas. It doesn't look like they are taken directly from the irrigation, neither from the rain. They have an isotopic signal very close to soil water, the first thing. And the second thing is that for all the profiles, they have a different signature, meaning that the interrow plant is uptaking water from the very first centimeters. Here it could be from 10 to 20 centimeters, but in general for all the profiles, it goes from 0 to 30 centimeters, and then the grapevine is always left to it and uptaking water from below that. So that's the type of information that with visual inspection we can see already from the isotopic characterization of the water. But if we want to put numbers on it, if we want to go beyond the visual comparison, then there is a variation mixing model called MIXIR that estimates the proportional contribution of the different sources to the mixture. So we said, okay, now our grapevines are uptaking the water mostly from the soil. Okay, we checked from each of the different soil samples which was the isotopic characterization. and we grouped those that were actually equal or similar. Each of the different groups, so we've differentiated the soil profile, let's say, here in 4 parts, right? Here in 3, because it was shorter, our soil profile, but here in 4. And then each of the signatures was significantly differently from the rest, from the next one. So having that and putting those numbers in within the Bayesian mixing model, it tells you an estimate. So these are not absolute numbers, but this gives you an estimate of how much this plant has taken from here, from here, from here, and from here, based on the isotopic number that it shows for the plant. So if we sum these numbers, these green numbers are exactly the same as these ones. It's the same proportions, it's the same numbers. So if we sum these Bayesian mixing model results together with the soil profiles from Manaki-Whenua and together with the soil properties that we've been checking centimeter by centimeter in the different profiles, we can come up with an explanation of why do the grapevines take the water from where, right? So for example, in the case of Selwyn, which is a fluvial recent soil, it's not well developed and it has plenty of water availability. So it looks like the uptake is fairly homogeneous across the whole profile. Instead of Awatere, which is also fluvial recent soil, it looks like it's mostly coming from these first 10 to 30 centimeters and then below 7 centimeters. And it really correlates nicely with higher sand content in those 2 layers. About Hinds and Demuka, they show more or less an expected behavior for grapevines in Verizon, which is going deeper, trying to get water, rely on water which is deeper in the soil to avoid evaporation from the first centimeters. And then we had this case here for our most mature soils. This is due, so the results are due because we couldn't, we found here the subcompaction, so a very hard layer. We couldn't keep, manually coring below that. Therefore, it shows that most of the water it's coming from these 2 layers of the soil. It's probably so it's probably not too far from reality, but it might look more like this one. This one, it was also a very hard soil, but we were using for this one an electric hack jammer, I think it's called. So an electric corer. So we could go below the hard pan. And it shows that the plants were uptaking water from below that as well. So probably they are still taking water from here, but we just don't have the samples to prove it. In any case, above any hard pan, it looks like the majority of the water is going to be taken, maybe because it's too hard for the roots to develop in such a compacted soil, which makes sense. So this is the first approximation. So this is the first result, let's say, that we have and that we can give to the need of improving irrigation efficiency and soil water management. We don't answer the question to improve irrigation efficiency and soil water management within Marlborough, but we start to understand and to put numbers and to know exactly where the grapevines are taking the water from in each of the soil types. And based on these results, we have some general best practices, which are, the first one is maintaining managed cover crops to enhance infiltration and water retention. They look that they are working well, they are doing their job. Remember that gravimetric water content was was correlated with organic matter and not that much with the finds with clay and silt, not that much with texture. And because we've seen that for all the profiles, the interrow grass was not competing with the grapevine. Then we also suggest to promote deep rooting throughout reduced shallow watering, because as we can see, most of the grapevines are taking water from farther below the topsoil, and tailoring irrigation scheduling to soil profile characteristics rather than applying uniform regimes, because we've seen that the water, each soil type has a very different mechanics. But as said, this is just an initial, very initial assessment or first step to get to this point. To get to this point, I think we can keep using isotopes to figure out, right, which are the irrigation efficiency measures in place that we can put. Why? Well, first is very obvious. We've only targeted 7 of the 16 soils, so we could do that for the remaining 9 soils. And the second one is that if you remember, our irrigation water has a signal which is very close to the groundwater. Therefore, we are not capable of differentiate. It's not significant, statistically significant, different from the groundwater. If we apply a water in the irrigation, if we apply a water that has a very distinctive isotopic signature, then we can see how much it infiltrates in the soil and how much is uptaken by the plant. That can be very easily done with, there's a lot of water that is altered either with oxygen or hydrogen. And it is actually, this is a brand which is commercializing it, is for you to drink. Actually, at least in Europe, like around 10 years ago, it was very trendy to drink demineralized water because for whichever reason it would help you with, I don't know what, because it was actually not good for anything, but it's not bad either. So it, and it's very expensive. So, but you can still buy it, and then you are sure that it's not going to be, it's innocuous. It's not going to be bad for the plant, for the wine. It won't alter absolutely anything. You just will have a very different isotopic signal, which makes it perfect for tracing irrigation water that we could not do this time. We are thinking about doing this summer back in Spain. Another thing that we could do is we could measure the water requirements throughout the key phenological stages at least, to know when the vines are starting to shift their uptake from shallower to deeper horizons. There are a couple of studies done, really like 2, around the world, and they already show that the grapevine shifts their uptake from shallower during spring towards lower in summer. There's another one going on in Waiheke Island, and that would be like really interesting to know when watering would be good to apply and at which depth. And lastly, isotopes also allow us to determine how soil management practices affect the root distribution and therefore the water uptake, which I think it can be also a potential interest in Marlborough, because through soil management you can already save a lot of irrigation needs. So actually, by continuing this type of study, we can potentially propose the irrigation efficiencies needed that I said in the beginning, which is something that it was already said by Steve Green, right? Which I believe it's a colleague of yours. Yeah, okay. In Palmerston North, maybe, or in Auckland.
It's a lot of that work was done here in Marlborough.
Right. He has a full chapter, I think, in this book, and it's for Marlborough, you're right. And he already proposed all of that in 2008. So it's more than 15 years ago that this need is in place. And I cite him directly. It's really small, sorry. But he says that wise water used throughout irrigation in vineyards and new adaptive water management strategies are urgently required. And he's talking about Marlborough. And he says that it needs to be identified how much water plants are using and when and how much irrigation is needed. So actually, by using this methodology, these needs would be answered. And lastly, he says that there is a scope for policy development, but that would be after having underpinning evidence. And that's what the isotopes of water can bring into the table in this context of Marlborough. And before thanking you, I would like to thank the people that made this project possible, because at least this project was, and research in general, I would say, it's a teamwork. I would like to thank my husband, who came here just to help me for the whole week. and a couple of master students, Lily and Mitchell, and then also Damien. Thank you for allowing us access to all the 7 vineyards, and Stuart, who came to the rescue with the automatic jackhammer after we broke 3 hammers trying to core the soil coring. So it was really, really hard. And thank you all for your attention.